75 million years ago, the Late Cretaceous plain stretched across what we now call the Gobi Desert. These landscapes were dotted with shallow riverbeds, sand dunes, and sparse vegetation, forming a semi-arid ecosystem bustling with life. Among the small but agile dinosaurs that navigated this terrain was one that would later become notorious in the history of paleontology, Oviraptor. The discovery of Oviraptor fossils in the early 20th century ignited scientific curiosity and controversy. Initially, paleontologists found an individual fossilized atop a nest of eggs. Interpreting the arrangement, early scientists assumed that Oviraptor had stolen the eggs. This misconception led to its evocative name, meaning egg thief. Yet decades later, more complete fossil evidence revealed a different story. These eggs were in fact Oviraptor's own, and the dinosaur was likely brooding and protecting its clutch, demonstrating behaviors strikingly similar to modern birds. Physically, Oviraptor was a medium-sized theropod, measuring approximately 1.5 to 2 meters in length and weighing between 30 and 40 kilograms. Its lightly built skeleton, long hind legs, and three-fingered arms indicate an animal adapted for agility rather than brute strength. The skull was short and robust, ending in a toothless, parrot-like beak that could crack hard-shelled eggs, capture small animals, or strip vegetation. Many paleontologists consider it omnivorous, capable of exploiting a diverse array of food sources to survive in a competitive ecosystem. Adding to its distinctive appearance, Oviraptor possessed a prominent cranial crest. This bony projection likely functioned in visual communication, mate attraction, and species recognition, suggesting that social behaviors played a significant role in its life. Closely related oviraptorids, including Citipati and Khan, shared similar crests, indicating that such features were widespread within the family. The ecosystem of the Late Cretaceous Gobi Desert was teeming with other dinosaur species. Agile predators such as Velociraptor stalked the sands, while plant-eating herbivores like Protoceratops grazed nearby. Even apex predators like Tarbosaurus dominated the food chain. Within this network, Oviraptor's size, speed, and adaptability allowed it to navigate both predation and competition. Perhaps the most revolutionary insight from Oviraptor comes from its parental behavior. Fossilized specimens clearly show the dinosaur positioned over eggs in a protective posture, similar to brooding birds. This evidence dramatically reshaped scientific understanding of dinosaur behavior, highlighting that parental care, once thought exclusive to modern birds and mammals, was present among non-avian dinosaurs. Oviraptor's combination of agility, omnivorous feeding, feathered body, and nest-guarding behavior paints a picture of a dinosaur remarkably bird-like in both appearance and lifestyle. Its existence bridges the evolutionary gap, showing traits that would later be refined in the birds that survived the mass extinction events at the end of the Cretaceous. The story of Oviraptor is not just about its anatomy or diet, it reflects a complex ecological strategy, integrating speed, intelligence, social signaling, and parental care to survive a dynamic and often perilous environment. In many ways, Oviraptor embodies the intricate balance between predation, survival, and reproduction that characterizes all successful species. Its narrative begins with the eggs, the nest, and the protected young, extending into broader evolutionary questions about the origin of bird-like behaviors. This is only the beginning of the journey, as subsequent parts will explore its nesting strategies, social interactions, feather anatomy, and evolutionary significance. As Oviraptor matured, its life revolved around a balance of foraging, social interaction, and vigilant protection of its territory and nests. The desert-like plains of the Late Cretaceous Gobi were unpredictable. Periodic floods reshaped riverbeds, seasonal storms swept across the open terrain, and volcanic ash occasionally darkened the sky. In such a volatile environment, survival depended not only on speed and agility but also on adaptability and keen awareness of surroundings. The toothless beak of Oviraptor was a remarkable adaptation. While it may appear fragile at first glance, it was in fact extremely versatile. Fossilized wear patterns on beaks indicate repeated use in cracking eggshells and hard plant material. Some evidence even suggests that Oviraptor may have consumed small vertebrates or invertebrates, supplementing its diet when vegetation was scarce. Its feeding habits show parallels with modern omnivorous birds such as crows and gulls, which can exploit a broad range of food sources depending on availability. Oviraptor's forelimbs were proportionally long and ended in 3 slender, clawed fingers. These limbs were probably used in a variety of ways, manipulating food, digging in loose soil, or even gently moving eggs within the nest. The flexibility of the arms suggests intelligence and dexterity beyond what might be expected from a dinosaur of its size. In many reconstructions, paleontologists depict Oviraptor using its feathered forelimbs not only for thermoregulation but also for display, communicating signals to potential mates or rivals. Feather impressions found in related oviraptorid fossils reveal a remarkable similarity to birds. Juvenile oviraptors were likely covered in a dense layer of downy feathers, providing insulation and camouflage. Adult specimens retained feathers primarily on their arms, tail, and possibly along the crest, creating striking visual displays during courtship or territorial disputes. These feather structures reinforce the evolutionary link between non-avian dinosaurs and modern birds, suggesting that complex plumage evolved long before the first powered flight. The cranial crest was another key feature for communication. The shape and size of the crest varied among individuals, likely serving as a visual indicator of age, sex, or dominance. Display behaviors may have included raising or tilting the crest, spreading feathers on the arms, or performing intricate postures to signal strength and reproductive fitness. Social behavior in Oviraptor may have been more sophisticated than previously thought, with complex interactions within small groups or family units. Nest protection was central to Oviraptor's daily life. Fossils reveal adults positioned atop nests in a classic brooding posture, wings partially extended to shield eggs. This strategy would have protected the developing embryos from both environmental extremes and predators. In some cases, multiple nests in proximity suggest that oviraptors may have nested in colonies, providing further safety in numbers and potentially facilitating social learning among young individuals. The eggs themselves were elongate and often arranged in pairs within circular nest structures. These patterns reflect careful planning, with each egg oriented to maximize incubation efficiency and minimize the risk of damage. Paleontologists studying oviraptorid nests have noted similarities to modern bird nesting strategies, indicating that careful reproductive investment is an ancient trait among theropods. The predator-prey dynamics of oviraptor's environment were intense. Smaller predators, such as Velociraptor, posed a constant threat, while larger carnivores, including Tarbosaurus, dominated the top of the food chain. Speed, camouflage, and group vigilance were critical defenses. Oviraptor's large eyes suggest keen vision, allowing rapid detection of predators and careful monitoring of its nest. Oviraptor's ecological role extended beyond survival. It helped shape the ecosystem. By consuming a mixture of plants, eggs, and small animals, it contributed to nutrient cycling and energy flow within its habitat. Its foraging behavior may have aided seed dispersal, insect population control, and soil aeration, playing a subtle but meaningful role in maintaining ecosystem balance. Despite the challenges, Oviraptor thrived for millions of years, illustrating the success of a strategy that combined agility, intelligence, social behavior, and parental care. Its story provides a window into the lives of small, bird-like dinosaurs navigating a world dominated by both giants and cunning predators. In addition, Oviraptor exemplifies the concept of convergent evolution, with many of its traits, feathers, beak, nesting behavior, mirroring those seen in modern birds, even though they appeared independently in different lineages. This demonstrates that natural selection often finds similar solutions to ecological challenges across vast spans of time. As the late Cretaceous sun rose over the rolling plains and sandy riverbeds of the Gobi Desert, Oviraptor moved with a grace and purpose that belied its relatively small size. Its long legs propelled it effortlessly across open terrain, each stride covering ground quickly and efficiently. In these ancient landscapes, speed and agility were not mere advantages, they were prerequisites for survival. The feathered forelimbs of Oviraptor were multifunctional marvels of evolution. Covered in long, filamentous feathers, they served as protective shields over eggs, as visual signals during courtship, and as stabilizers while navigating uneven terrain. Juveniles were likely cloaked in down-like feathers, insulating them against temperature fluctuations and camouflaging them from predators. Adults retained feathering along the arms, tail, and sometimes the cranial crest, emphasizing social and reproductive displays rather than insulation alone. The eggs themselves were an intricate marvel of natural engineering. Elongated and arranged meticulously in circular patterns, these eggs demonstrate a remarkable understanding of space and resource allocation, even in the absence of complex cognition as humans define it. Fossil evidence suggests that Oviraptor would adjust its posture, subtly repositioning eggs and shielding them with partially spread arms, a behavior strikingly reminiscent of brooding birds millions of years later. Oviraptor's beak played a central role in its daily routine. While toothless, it was robust, capable of cracking hard-shelled eggs and consuming a diverse diet that included plants, small vertebrates, and invertebrates. Microscopic analysis of fossilized jawware indicates repeated use in manipulating food and possibly interacting with nestlings. The versatility of this feeding apparatus reflects an opportunistic and highly adaptive lifestyle, one that allowed Oviraptor to exploit the dynamic and sometimes unforgiving ecosystems of its era. Its cranial crest, far from being a mere ornamental feature, was a hub of social interaction. Differences in crest shape and size among individuals likely communicated age, sex, and social status. Paired with feather displays and deliberate posturing, the crest contributed to complex behavioral signaling. Courtship rituals may have involved coordinated movements, head tilts, and subtle feather flaring, creating a visual language within oviraptorid communities. The surrounding ecosystem presented both opportunities and dangers. Contemporaneous dinosaurs like Velociraptor were swift, predatory threats, while herbivores such as Protoceratops moved in herds, altering the environment and occasionally providing feeding opportunities for omnivorous opportunists like Oviraptor. Apex predators like Tarbosaurus ensured that vigilance and caution remained constant imperatives. Despite these pressures, Oviraptor demonstrated extraordinary behavioral sophistication. Its nesting strategy, including the protective brooding posture and potential communal nesting, highlights an evolutionary emphasis on offspring survival. These behaviors not only enhanced the survival rates of the young but also fostered a social dynamic among adults, balancing competition with cooperation. Feathers and social signals intertwined to shape interactions within Oviraptorid groups. Subtle shifts in arm position, the angle of the crest, or the spread of tail feathers conveyed intention and status. Modern birds exhibit similar behavior, and Oviraptor provides a remarkable early example of this type of communication. From an evolutionary perspective, Oviraptor offers insight into the transition between non-avian theropods and early birds. Its combination of feathers, brooding behavior, and bird-like skeletal structure underscores the continuity of traits that would eventually culminate in the avian species we see today. The careful guarding of eggs, the display-driven crest, and the flexible diet reflect adaptive strategies that were highly successful over millions of years, yet ultimately subject to the catastrophic events that would reshape the planet. As it navigated its semi-arid habitat, Oviraptor contributed to the ecosystem in subtle but significant ways, controlling insect populations, dispersing plant seeds, and influencing the behavior of other dinosaurs through both predatory avoidance and social interaction. Every action, from foraging to nest care, was embedded in a complex network of ecological relationships. Thus, Oviraptor embodies the intricate balance of survival strategies, environmental pressures, and evolutionary innovation. Its story illustrates how a relatively small, bird-like dinosaur could thrive in a world dominated by giants, all while laying the foundation for traits that would persist in the avian descendants that survive to this day. The narrative of Oviraptor ultimately illuminates one of paleontology's most profound revelations. Non-avian dinosaurs were not distant, reptilian curiosities, they were active, intelligent, and remarkably bird-like. Oviraptor, with its feathered body, delicate yet versatile beak, and intricate nesting behaviors, exemplifies the evolutionary bridge between dinosaurs and modern birds. Fossil evidence of brooding oviraptors, combined with the sophisticated arrangement of eggs in nests, demonstrates that parental care, once thought unique to birds and mammals, was well established in theropods. The partially spread arms over the eggs, feathered covering, and attentive postures show behaviors that parallel contemporary avian incubation strategies. These findings profoundly reshape our understanding of dinosaur ecology and social behavior, revealing a level of complexity long underestimated. Oviraptor's ecological niche was equally remarkable. It was omnivorous, opportunistic, and highly adaptable, capable of consuming plants, eggs, insects, and small vertebrates. Its feeding behavior helped regulate populations of smaller species, contributed to nutrient cycling, and influenced the structure of its ecosystem. By foraging alongside larger herbivores, Oviraptor may have capitalized on disturbed vegetation or exposed prey, demonstrating a nuanced understanding of resource exploitation within its environment. The cranial crest and feathered limbs were not merely decorative, they were integral to social signaling, mating rituals, and territorial displays. Differences in crest morphology and feather patterns likely communicated information about dominance, age, or reproductive readiness. Such visual communication illustrates early forms of social sophistication, emphasizing that Oviraptor was far more than a simple, instinct-driven creature. It was a dynamic participant in its ecosystem, interacting continuously with both its own species and others. From an evolutionary perspective, Oviraptor embodies the traits that would later be refined in birds. Feathers, brooding behavior, lightweight skeletal structure, and visual displays form a suite of characteristics that link it to avian descendants. Although the mass extinction at the end of the Cretaceous wiped out Oviraptor itself, its lineage reflects broader patterns of adaptation and survival. Smaller feathered theropods with similar traits endured the catastrophic events, eventually giving rise to the birds that now populate the planet. Modern birds, in essence, carry echoes of Oviraptor. The nesting behaviors, feather arrangements, and foraging strategies observed in living species can trace conceptual lineage back to dinosaurs like Oviraptor. Observing a bird carefully tending to its nest, flaring its plumage, or selecting diverse foods reveals behaviors that had already evolved tens of millions of years prior in these small, bird-like theropods. Oviraptor's legacy is not limited to evolutionary biology, it also offers insight into the dynamics of prehistoric ecosystems. It highlights the interconnectedness of species, the influence of behavior on survival, and the intricate strategies required to navigate both predation and competition. In doing so, Oviraptor provides a window into the delicate balance of life that existed in the Gobi Desert during the Late Cretaceous. The study of Oviraptor continues to evolve with new fossil discoveries and advanced imaging technologies. CT scanning and microanalysis of fossilized bones reveal details of growth rates, musculature, and brain structures, further enhancing our understanding of its sensory capabilities and behavior. Chemical traces in eggshells and bones offer tantalizing clues about diet, metabolism, and environmental interactions. Each scientific advance adds depth to the portrait of this extraordinary dinosaur, reinforcing its importance as a subject of study. Ultimately, Oviraptor represents more than a single species. It symbolizes the remarkable continuity of life, illustrating how traits honed in a prehistoric desert could echo through evolutionary time to modern ecosystems. Its story is one of adaptation, intelligence, and parental devotion, an emblematic example of the sophistication of non-avian dinosaurs and the evolutionary processes that gave rise to the birds we know today. In the vast narrative of life on Earth, Oviraptor reminds us that even small, seemingly delicate species can exert profound influence, shaping ecological communities, guiding evolutionary trajectories, and leaving legacies that endure for millions of years. Observing its fossilized remains is akin to listening to the whispers of a vanished world, a world in which survival demanded both skill and subtlety, and where the seeds of modern avian life were quietly taking root.